This is problem number 16 on your homework paper. So, what do? This blue part is the graph for y equals x minus 2 square root. If I have a negative sign out in front, what does that do to my graph? Flips it. This one right here is negative x minus 2. I'm sorry, both of these have a plus 1 on them. So when you graph the positive square root and the negative square root, do you see that you get a whole parabola by graphing both of the pieces to this? That's why when you're finding the inverse, it has to say plus and minus so that you have a whole entire parabola. And so this is going to be, since I'm looking at this, I'll go ahead and finish it. That would be the domain and range for this one. And the domain is going to be this. And the range on this one is flipped because it is a reflection. And so that is the domain and range for the. That's interesting. Okay, and so this is our notes. This is on the blue notes that's labeled part 1. And so we have a new graph to look at. This parent graph is called the cubic graph. Excuse me. It is f of x equals x to the third power. And so to figure out the graph, you can make a table. So I'm going to start with negative 2. And this graph says to raise it to the third power. So what's negative 2 times negative 2 times another negative 2? Otherwise known as negative 2 to the third power. And multiply that out with your calculator. Negative 1 times negative 1 times negative 1 would be equal to 0 times 0 times 0. The reason I am repeating myself is this function says I am raising it to the third power. 1 times 1 times 1 is still 1. 2 times 2 times 2 is 8. And those are the points. I need you to make these points on your graph a little bit larger so you can see these. These are the key points that you need to memorize for a cubic function. Because it has arrows on both ends, the domain is positive infinity to negative infinity. I should have said it the other way around. It's negative infinity to positive infinity. These key points and these key attributes in this chart are things you need to memorize. This is one of your parent graphs. And so the domain is all real numbers. The range is all real numbers. It has one y-intercept at y equals 0. And it has one x-intercept at x equals 0. And it has rotational symmetry. What is rotational symmetry? About a point. And it has rotational symmetry around this point. Put your pencil on the point 0, 0. Put your pencil on the point 0, 0. We are waiting for some of you to pick up your pencil. And rotate your paper upside down. Turn your paper so that it's upside down. Now, I'm not turning mine so you can compare it. Now, when you turn your paper upside down, doesn't this graph look the very same as this one that's right side up? When you rotate your paper 180 degrees, it looks the same. That's what rotational symmetry about a point means. It's about a point because I told you to hold your paper down right here. So that's what it means, rotational symmetry around a point. This has 180 degrees rotational symmetry, and if you rotate it 180 degrees, it looks exactly like it did. And then we have the same transformations that we have done over and over and over again. If this has a x minus 4 in parentheses, what's that going to do? If it has plus 2 in parentheses, that's going to go to the left. If it has a plus 3 that's not in parentheses, that's going up. Minus 5, not in parentheses, that's going down. It's the same thing as we have done on many other graphs. So, in this example number 1, we are comparing to the parent graph. What does the parent graph look like? Well, that's the very first one on this other paper. That's the one that goes with this table. This table goes through 0, 0, and 1, 1, and 2, and 8 would go off of my chart. And so this is the parent graph that I'm comparing this one to. Parent graph, transformed graph. Well, what's been transformed? The parent graph goes through 0, 0, and this has a, I can't really call that a vertex point, but this has a key point right here. So what's happened to it, if I start here and move it here, have I moved up, down, left, or right? Right, 1. Didn't move it up or down. The parent graph from the table, the next point on the table from 0, 0 is 1, 1. The parent graph goes over 1 and up 1. Does this graph go over 1 and up 1? Does it go through this point right here? That's because it's been stretched. This point right here is the next pretty point on my graph. Please add that into your graph. This transformed graph goes through the point 3, 4. So that means it has been stretched. What am I going to need right here when I write an equation? What am I going to need to stretch the graph? A number at the beginning. We call that number A. To get A on that salmon colored paper, you did rise over the square root of the run because those were square root graphs. On these graphs, A is going to be equal to rise over run to the third power. Where did the third power come from? It came from the parent graph. So, rise over run to the third power. So the A is going to be 4 over 1 to the third power. What is that equal to? Just 4. 4 over 1, but we'd reduce that to 4. So this is going to be 4x minus 1 to the third power because x is still a liar. If it goes to the right, it's x minus 1 in parentheses. The third power, because a curve that looks like this is a cubic graph, it is x to the third power. The domain is going to be easy on these. The domain and range, not on all functions, but the domain and range on the cubic function is negative infinity, positive infinity, because it has arrows at both ends. Yes. 2. Ah, yes, I'm sorry, I miscounted. Did this move over 1? It did not. How far did it move over? 2. And so would you please fix that? Because I think I said 2 and wrote 1. Did you fix it? Okay. So over here on this graph right here, we're comparing to the parent graph. The parent graph goes through 0, 0. This has this point right here. It's actually called a point of inflection, where you turn from a curve going that direction to a curve going this direction. And so how much has it moved from here to here? Has this one been stretched? The parent graph goes over rise over run 1 over 1. Does this one go rise over run 1 over 1? So that means the A is 1 over 1 to the third power. Well, what's 1 over 1 to the third power? It's equal to 1. So this would be 1 x minus 0, because it didn't go left or right, up 3. This is a third power because this is what a cubic graph looks like. And the domain can be written negative infinity to positive infinity. But another way to write that is all real numbers. So you can write the domain in range this way or that way. It doesn't matter. Now, back up here to this function, though. When you multiply by 1, does it make it more or less, or it stays the same? It stays the same. So usually we don't write the 1. Now, this minus 0, when you subtract 0, does it make it more or less, or it's the same? So we usually don't write a minus 0. So this would be considered better form. Both of these are correct answers. This would be considered to be better form. So, what does it mean if I have a negative sign out in front? A negative sign out in front flips it over the x-axis. What's a better mathematical word instead of flips? Reflects it over the x-axis. To reflect over the x-axis, copying, we would take this original table on the front page and multiply this column by a negative 1. And so that would make this positive, positive. A negative out in front multiplies my y numbers by a negative 1 compared to the parent graph. And so this is going to go off my chart a little bit, but you can tell where it ought to be. And this would be negative 1, positive 1. Now, this is not the correct way to make a cubic graph, so don't copy this. This does not connect the dots and make a straight line right here. That is incorrect. This curves up and this curves down. The reason I know that is in the past I have graphed decimal points in between the 0 and the 1 to see what it goes in there, and you could do that if you so choose. Okay, so that is a reflection over the x-axis. The parent graph this is what the parent graph would look like. I've sketched it in there very lightly. Can you tell that this one points up The reflection points down. This one points up. It's a reflection of this one that points down. This is the parent graph. This is the reflection graph. But what does a negative sign right here do? Where it's in parentheses with the X. So, how do you do that? Keep up. How do you make this reflection over the y-axis? To make a reflection over the y-axis, do you know what I'm looking at? This is the first page. To make a reflection over the y-axis, the y numbers are going to stay the same, and the x numbers are going to multiply by a -1. So that is the table for a reflection over the y-axis. So this 2 is going to go with -8. So, and this we're going to make a curve right here. And we're going to make this curved. And this is a reflection over the y-axis. What do you notice about a reflection over the x-axis and a reflection over the y-axis? It's the same. Because of that point symmetry that we talked about on the first page, these reflections are the same. Now, sometimes, for obvious reasons, people get confused about the notation that is used here with transformations. What does a number out in front do to the transformation? It makes a stretch. If you want to be technical, it makes a vertical stretch. What does a +3 at the end do? Up 3. Those are the transformations. Now, this does not tell you which graph I'm transforming. This says for whatever graph, for every graph, this stretches, this moves it up. This is called function notation. Please write that down on your paper. This is called function notation. If I take that function notation and apply it to this specific graph, this is called function equation because there is an equal sign. So please label those so in your notes you will know what the difference is between a function notation and a function equation, because for obvious reasons, because they both start with function, they are easy to get mixed up. The domain and range for this specific function is -infinity to +infinity for the domain and the range. This is called function notation. If I apply it to this specific function, this is -x + 1 to the 3rd power. What does the negative sign tell me to do? Whether I have a generic function or a specific function, the negative out in sign tells me over x. What does the +1 tell me? Left 1 because x is still a liar. Whether it's in this form or this form, it's telling me left 1. If I'm talking about this particular function, the domain and the range can be written like that, or it can be written with the all real number system. You do not have to write it both ways because I did say or. Is that the end of the blue notes? We are very quickly going to look. Now, do you see that this second part starts exactly the same way? You have the exact same graph, the exact same table, the exact same attributes. The domain and the range are all real numbers. This is on the white one. Are you in the right place? Now, if I want to find the inverse of this graph, the inverse of this graph, I'm going to have to put it in y equals notation, and then how do you make an inverse? And solve for y. In order to solve for y, I have to get rid of the 3. How am I going to do that? Well, if it was a 2, you would take the square root of both sides. If it's a 3, you are going to take the cube root of both sides, and that's how it's written, and we'll be talking a whole lot more about what it means very shortly. But the cube and the cube root cancel each other out, and so this is called the cube root, and it is the inverse of the cube. If you have a table, how do you find the inverse for a table? Same thing. What do? Switch the x and the y. So down here, I am going to switch the x and the y. And so this would be -8. So I'm looking at the table up above, and I am switching the x and the y. And that's where they got these points for this graph right here. The domain here is still all real numbers. All of the attributes for the cubic function also apply to the cubed root function. The difference is this one points up and this one points which way? Nope, right. And because it has been reflected over the y equals x line, these have switched places.